So, hello everyone, good evening, and welcome back to the week 11 of NPTEL TA live interaction session. So, this is the second last week for this course on rapid manufacturing. The course ID for this course is noc22-me74. This is Palkin Gupta, a PhD scholar and a PMRF scholar in Department of Material Science and Engineering, IIT Kanpur. And the course instructors for this course are Professor J. Ramkumar and Professor Amandeep Singh, Department of Mechanical Engineering, IIT Kanpur. I hope all of you are enjoying as we are moving forward in this course. I think we can start with this week's content. So we'll briefly cover what has been conducted in lectures during this week. Okay, and then we'll perform some sample problems. Okay, so let us begin. So this week it started with a rapid product development. Okay, so can I ask Mr. Kavi to tell me what was rapid product development very briefly? Am I audible, Mr. S. Kavya Raslan? Okay. Okay, so in rapid product development, we have main features as Cad and Cam. We can realize this rapid product development because of the computers present today. So, what is Cad and Cam? They are computer aided design and computer aided manufacturing. Okay. So it is a technology which is majorly concerned with the use of computers to perform your design and manufacturing functions. So it is this technology is concerned with the use of computers for designing and manufacturing functions. So these days you must be seeing around that there are a lot of softwares which allows you to develop 3D CAD models, and there are softwares through which you can control your machines to perform specific commands. Sorry. So this chart summarizes the CAD and the CAM process. So everything starts with the need for a design. And how does the need arises? Because of the different specific requirements of the humans or the any person. Okay, and as per the needs, the design there are design definitions. Its specifications are set and requirements are also set, as we had studied in first 2 weeks of the course. Then all the specifications and the requirements are collected, and there are relevant designs developed based on these requirements and specifications. Okay, and then this design is taken to the conceptualization stage. Okay, where actual models are developed, and this particular requirements, it is checked if a particular design is satisfying those requirements, or proving the concept for which it has been designed. And then comes the design modeling and simulation. Okay, and then finally you model that and simulate it to check if it is a feasible design or not. So till here is your synthesis part. Okay, now you have developed a product, you have a design. Now you analyze if it is feasible for a particular function or not. Okay, so analysis is done to check if the specific design can meet the requirements of the user or not. Alright, now in this analysis, first you analyze what are the stress concentrations, if there are any stress risers present there, or what are the strains. Okay, then you optimize based on your simulation results, stresses and strains, you optimize that design and then again evaluate it, and then once it is done, you finally document the design, and then you communicate it to the department concerned with its manufacturing. Now in the manufacturing process, that is the CAM process, computer aided manufacturing, your process is planned, like how you are going to design how that particular design is to be turned into a product. So say be it like you need to turn it first, then you need to drill some holes, okay, and then you need to finish it, something like that. Okay, so you decide the sequence of events is decided. So now this process planning consists of production planning, design and procurement of tools, order materials, numeric control, computer numeric control or direct numerical control programming. And using these all techniques, the product is finally produced, checked using CAQ, computer aided quality control or inspection. And once it passes the quality control, it is sent for packaging and then shipping, and then it is marketed to the final end user. And based on the reviews, we again have a new design requirement. So moving ahead, implementation of a typical CAD process on a CAD CAM system. So first we delineate a geometric model, then we transfer, then there is a definition translator, and then we have a geometric model. Okay, so firstly it is decided what is to be made, then its definition is translated to a software, then you finally make a geometric model, and then you have interface algorithm to interface the geometric model with the analysis algorithm. Okay, so then you go to the design and analysis algorithm, where it is checked if your design is feasible or not. Okay, and then it is sent to the CAM process. So if it is found that your design is not feasible, if not feasible, then the process starts all over again from the delineation of geometric model. So there are different tools that are required to support the design process. So for design conceptualization, you require geometric modeling techniques, graphics aid, manipulations and visualization. For design modeling and simulation, same as above, but for simulation you need some animations as well, wherein suppose you want to animate how a screw is moving into a hole. So for that animation purposes, you require certain special modeling packages. Then there is design analysis, where you require analysis packages like the stress analyzers or strain analyzers, and there are certain customized programs and packages as well. Then you go to design optimization. Based on the results from the above analysis, you optimize the design. So suppose you have a cube, and there is lesser stress concentration in the middle, and you don't need the middle part, actually it is not supporting anything, so you can just get rid of this part, so that will save you of the material. And then the design communication and documentation. Okay, now similarly a CAM process is how a CAM process is implemented. So you have a geometric model, then there are interface algorithms that helps you to interface between your software and the machine. which is going to manufacture your component. Then your process is planned, and then numeric control programs are defined. So these are numerical control programs. That is then after your product is made, then it is inspected for quality, then it is assembled and packaged, and then it is shipped to the market. Now, what are the different tools that are required, the CAM tools in design process? So process planning. So for that you need a CAPP, which is computer aided process planning. Okay, cost analysis. In any time you want to minimize the cost. Nobody wants to pay extra for a particular component. Then material and tooling specification, they have to be decided. Then part programming, which is NC programming. Then inspection, which is computer aided quality and inspection software. And then your assembly, which is robotic simulation and programming. You can just simulate your entire plant or assembly lines using certain softwares. So plant simulations. Simulation as in, like, you can simulate how your entire plant will work, like how your product will go from stage 1 to stage 3 in a particular plant. Now there are certain CAD standards and standardizations in graphics. Now, why are these CAD standards required? So can any one of you answer? Mr. Vedant, are you available? If you can tell why CAD standards are required. If your mic is not working, you can type in the chat box as well. Okay. So, certain CAD standards and standardization in graphics is required so as to ease out the exchange of CAD data between multiple platforms. So, your CAD needs to travel from your software 1 to software 2 to machine 1, machine 2, and to machine N. So that everything remains compatible with each other and there are no changes in the CAD data when you transfer data from one software to another and to one machine to another. You require certain standards so that the format of these CAD files is a neutral one, that is independent of the platform. Okay, so there are certain standards that had been listed out. So first is GKS, graphical kernel system. So GKS is basically, it provides a complete range of graphical facilities in 2D. Okay, so it this is for provides a complete range of graphical facilities in 2D. Okay, including the interactive capabilities. And its function is to control the all types of graphic devices such as plotters, displays, etc., and they should be small enough uh, for a variety of programs. Okay, so basic graphics that are available in your GKS systems are your bar, so a simple bar. So it provides you 2D facilities, an arc. So you have an arc, then you have a pie slice, okay, or a quarter of a circle, or a full circle. These are some of the examples. Then some other was FIGS, like Programmer's Hierarchical Interface for Graphics, Code, GKS, 3D. Now there is one IGES format, which is Initial Graphics Exchange Specification. So it is the most comprehensive standard, and it is designed to transmit the entire product definition. Sorry. So it is the most comprehensive standard and is designed to transmit the entire product information including that of manufacturing, and any other associated details. Okay, so IGES is the most comprehensive standard, as along with the CAD data or the solid geometry, it also transmits the information about the manufacturing process and all the other relevant details. Okay, so it is like one of the most comprehensive standards. Then is your DXF, which is your drawing exchange format. So this has been developed and supported by Autodesk for use with the AutoCAD drawing files. So it facilitates the transfer of drawing files. It then comes your STEP, which is a standard for the exchange of product model data. So it is a format, it represents the information necessary to completely define a product throughout its entire life. Contains information necessary to completely define a product throughout its entire life. Okay, that is from the product conception to the end of useful life. Okay, and these methods have evolved over time. Now there are, sorry, this was for STEP. Another is DMIS, which is Dimensional Measurement Interface Specification, and this is a pretty new interface for manufacturing. That is your VDI, Virtual Device Interface, and many more interfaces are available. Now comes the geometric modeling. It is the central part of a product design. Without geometric modeling, you cannot proceed for the design of a product. Now, what are its different functions? So the configuration of solid must stay invariant with regards to its location or orientation. So this means that if you are having a cube, it should remain a cube even if you change its position or orientation. It should have an interior and must not have any isolated parts. For example, this is your one solid and this is your another part. So if these are isolated here, so this doesn't constitute a single solid model. This is not. Must be finite and occupy a finite shape only. So although the solids can have infinite number of points within them, but their volume needs to be finite. Okay, volume of solid needs to be finite. Application of a transformation or other operation that adds or removes a part must produce another solid. Okay, so for example, you are having a cube and you have given this cylinder for subtraction. So ultimately what you will be producing is this kind of a part. So here is your this hole, a through hole. So this is also a solid. Okay, this is also a complete solid. Model of solid in Euler space may contain infinite number of points, as I mentioned just now. That in Euler space it may contain infinite number of points. Make sure points. However, it must have a finite number of surfaces which can be described. So inside this cube, you can define infinite number of points. Infinite number of points can be defined within this cube. But it has definite number of surfaces, that is, it has 6 faces, a definite number, which is the requirement, and hence it has a fixed volume. And boundary of the solid must uniquely identify which part of the solid is exterior and which is interior. So this boundary, say this is it should not be an ambiguous one. So this boundary needs to define that this is your interior part and this is your exterior part. So this should be able to define the regions, different regions of the any solid model completely. Now let us come to different types of geometric models. We have seen what are the functions and why is it needed. Now let us check what are the different kinds of geometric models. So we have first a two-dimensional models and three-dimensional models. I suppose I need not to explain them. So this is in 2D, this is in 3D. Now we have a wireframe model, a surface model and a volume model. So in a wireframe model, different points are connected using wires or lines. So this is P1, P2, P3, P4. Then comes your P5, P6, P7, P8, P9. Oh, this is not a point, sorry. P9, P10, P11, P12. So like this, it has different points. In surface model, we have different surfaces that join together to form a solid. So you have this starting from surface 1, then you have this surface 2, then you have this one surface 3, surface 4, surface 5. Now behind this on the other side, this is surface 6, this back surface is surface 7 and this bottom surface is surface 8. And next you have volume model wherein the different volumes of solids are joined together. So this is volume 1, this is volume 2 for two cuboids. Okay. Now what is the comparison? So in comparison, we have automatic view generation, which is all perspective or orthographic. It is impossible in line model and in surface model, but in volume it is possible. Cross sectioning in line model is manually guided and surface model is also manually guided, but in volume model it is possible. Even automated cross hatching is possible. Elimination of hidden details in wireframe, it is manually guided. It might be possible in surface model, depends on the geometry, but it is possible, clearly possible in volume model. Analysis functions, geometric calculations, difficult or impossible in line and surface, but possible in volume. And numerical control application, it is difficult or impossible in line, automatically possible in surface and volume. So we see variety of features are possible only in the volume model. So now, what are the different geometric construction methods? So using these geometric construction methods, we convert 2D geometry into a 3D one. So there are two methods. First is linear extrusion or translation sweep, and then other is rotational sweep. Can anyone define any of these methods for me? Mr. Vedant, can you define either translational sweep or rotational sweep? Or Mr. S. Kavi? Okay. So in linear extrusion or translation sweep, what we have is, so the baseline for both of these methods is that we are having a 2D geometry. So for example, let us take a 2D geometry like this. So we have a 2D geometry consisting of two different rectangles like this. Now if I extrude it in a z direction, so this is my z, x, y, supposedly this. So if I extrude it perpendicular to the plane of the screen or paper, so it will become a 3D model. So it will be something like this. Correct? Okay. Sorry. It will be something like this. Alright. Okay, so this is your now 3D part. So you have extruded in the Z direction. Okay, so this is your extrusion. So you have basically translated the, okay, in translate, Mr. Vedant has written in transitional sweep, we elongate surface plane of any 2D design to make it 3D. It is generally done in AutoCAD. Yeah, correct. So you have other softwares as well. So you translate this or elongate the surface plane in from a sketch in 2D to 3D. Now coming to rotational sweep. So in rotational sweep, what is that? You have a 2D model, your 2D sketch, and that is rotated along a particular axis to have a full solid. So for example, uh, this is your central axis or rotational axis. Taking a simple example of a sphere, if you have a semicircle and you rotate it about this axis, you will get a complete solid sphere. Okay. Okay. So in linear extrusion or translation, You translate it and along a one direction, and in rotational sweep you rotate it about an axis. Okay, so some of the primitives that are available nowadays in various modeling softwares can be cones, cylinders, wedges, torus structures, hemispheres, spheres, etc. Now, how do you create a solid with 3D primitives in solid modeling, or construct, which is mainly constructive solid geometry? So suppose you have to develop this complex part. How are you going to approach about it? So first you have this block. So this is your basic shape. If you take this as your starting point, you have a complete solid block. Now you add another block, union of it at the bottom face. So you get your basic outline of this entire object. Now you see there is one cylindrical hole slot in this. So you subtract. This is your union. This is subtract. You subtract this cylinder from this geometry. So you get this kind of a geometry. Then you see here is one slot. This is your slot. So you again take a cuboid, since this slot is of cuboidal shape. And then you again subtract it from this geometry. Okay, this geometry minus this block. So you get your this kind of geometry. Now you see there are two cylindrical holes on the side flanges. So you take two cylinders and then again subtract them. So then you get your final geometry. So these are all your Boolean operations which are used to generate a complete solid from your primitive geometries. Now we come to freeform surfaces. So first we have the Schoon's surface generation. So it is a simple surface which can be described by means of simple formula. So and then interpolating between those these formulas generate curves, and then these can be interpolated to get a surface. Now you can use these surfaces as it is in the form of different patches. These can be used as it is in the form of patches. Now what are Bezier curves? Okay, so can you explain how these are changing from this geometry, to this geometry, and then to this geometry? What is the change, Mr. Vedant? What is the change from geometry 1 to geometry 2 and to geometry 3? Why is the shape of curve changing? Okay, so in Bezier curves, we define certain control points. Now, these control points approximate the curve for us, and it is uh, not necessary that your curve passes through your control points. Okay, the curve necessarily passes through first and last point, but doesn't need to pass through control points. Now in cone surface, we had to use the surface as it is and we could not change it. But then Bezier curves came wherein by changing the positions of these control points, we can change the curve. So now when you pull this P1 to this position, so you have a change in the shape of the curve like this. So it is because of the change in the position of the control point. Change in position of control point, and which causes change in curve shape. Now from here you take your P2 point here, or more towards this side, and you take your P1 point here. So you come to this third configuration. Now your curve has changed to this shape. So because you have changed the location of your control points. Now comes the B-spline curves. In this, these are your control points. Okay. B-spline curve we are talking about now. Okay, these are your control points. Now this is your control polygon, this one in purple color. This is your control polygon and this is your curve, green colored one. Okay. Now it's B-spline curve, it generates a piecewise parametric polynomial curve. It generates a piecewise parametric polynomial curve. That is, uh, this has distributed this curve into small pieces, these 4 pieces, and now each piece is approximated by a parametric polynomial. Okay, here this entire curve was defined by single equation, but here it has distributed it into different pieces, and then here they are defined by individual polynomials whose degree can be selected by the user. Now, what is constraint based modeling, which is often called as parametric modeling? Most of the time, the modeling starts with a sketch in 2D and then swept along a specified direction to produce the desired component, which is also called linear extrusion, like we have seen just now, or translational sweep. Okay, so this is one of the examples from the lecture videos only. So this is one of the components whose 2D sketch is made and it is fully dimensioned and constrained. Fully constrained and dimensioned. Yes, you see, there is not even a single line or a part which has not been defined, and then you just extrude it in a direction perpendicular to the plane of the paper and you will get this solid component. Okay, so this is what is constraint based modeling. Now we have different types of solid modeling. We have boundary representation, which is basically the representations of the boundary of a solid in the form of different surfaces. So suppose this is your solid, this small one. Now if you take out each surface of it, so these are its boundary, individual boundary. So when your solid is represented in terms of these boundaries, it is called boundary representation. Okay, so solid is represented by means of bounded faces, and bounded faces are represented by means of edges and vertices. Okay. Then there is constructive solid geometry, which we have seen, which uses Boolean operations on primitive solid geometries to obtain the final part. So what is primitive solid geometries? They are basically your known solids, simple solids like cube, cuboids, cylinders, spheres, cones. They are generally termed as primitive solid geometries. Then you have cell decomposition, wherein you can decompose your entire solid into cells. Then there is spatial occupancy enumeration. So here your object is represented by a list of cubical disjoint spatial cells. Okay, so it is represented in the form of these small cubes, which then join together to form the entire solid. Okay. Then you have primitive instancing, wherein your object is represented by a set of solid primitives, and each primitive is defined parametrically. So the defined in terms of solid primitives like cubes, cuboids, cylinders. So it can have this one cuboid, second cuboid, and one cylinder. So three primitive solid geometries. Okay. Now comes the last. Now let us come to the last lecture, which was rapid product development. So this rapid product development, basically it is a manufacture culture which promotes the new product development from design to manufacture in the shortest time scale possible. So promotes new product development in shortest time scale possible with the use of uh, computers basically. So now this culture uses new technologies like the emerging 3D technologies, CAD cams, rapid prototyping, rapid tooling, rapid manufacturing, and along with the new management techniques to restructure the entire manufacturing process, so that your time from product to market, so that your time from design to market is shortened as much as possible. So now this rapid product development allows various companies to launch new products in a shorter span of time. Okay, and it has also reduced the cost of development of products. Like you can have small prototypes with the use of additive manufacturing, which can help you estimate the strengths. Now, computer simulations along with rapid prototyping technologies represent important tasks in different areas of industrial development because of their potential for cost saving and time saving. So, with the use of computer simulations, you can quickly check and analyze quick analysis of the feasibility and functionality of a particular product. And with rapid prototyping, it becomes really easy manufacture variety of components and designs. So you can make as complex designs as possible, and you can have them in different materials, or you can have them in functionally graded materials, etc. Now this is basically simulating reality with FEA. What is FEA? This is finite element analysis. It starts with simulating just the geometry rather than simulate both the geometry and the physical behavior, that is the functional behavior. So first you start with simulating the geometry, if it is appearing as it should or not, if it is giving an aesthetic appearance or not. Then you move on if a particular load is applied under static condition, if it is able to bear all the stresses and loads or not. Then you go to its actual dynamic behavior. Now, the different objectives for this are creating simulations. These can be static stress, thermal simulations, fatigue. Then you can have dynamic stresses. Then you can have modal frequencies and many more. CFDs, fluid dynamics problem. Then you need to assign proper materials if you are dealing with aluminum or stainless steel or say some polymer or polyethylene or polylactic acid, etc. Then you need to properly and carefully set the constraints and your loading conditions, and then you should be able to interpret your simulation results. But this simulation technique is a type of GIGO, which is garbage in, garbage out. So you need to carefully create your simulation, carefully build in the models that you think would approximate the real world situation more closely. If you give in some erroneous inputs, then all your results will be erroneous. If you give in accurate inputs, your outputs will also be more accurate in nature. Now this was one of the examples taken in the lecture. So this was a lever for some product, and the objective was to reduce the print time, the cost, and consider the material usage and alternative materials. So for this, firstly a CAD geometry was to be made. Then there was selection of materials. So two were considered, one was polystyrene and the other was ABS, where polystyrene was hard in wear and had high thermal resistance in comparison to ABS, but ABS was more cost effective and could be printed quickly. ABS was acrylonitrile butadiene styrene. Then once you have the geometry and you have selected the material, you go towards meshing. Okay, so meshing is discretizing this geometry into small parts. Okay, so first there are different kinds of elements that can be used to discretize this. So first one is tetrahedron, then it's a pyramid, then triangular prism, then hexahedron, each having a different geometry, different surfaces. And there is then we had tetrahedron element, and we can have variations within these single elements as well. So this is a linear tetrahedron. So how it is linear? So the approximating curve between these different nodes or vertices is a linear one. It is being approximated just by 2 points. Okay. Now this is your parabolic tetrahedron. Why? Because there are 3 nodes approximating each edge. Okay, so 3 nodes means a quadratic equation would define 3 points you can have a quadratic equation defined. So that is why it is giving you a parabolic one. So it is a 10 noded element. So 1 2 3 4 5, 6, 7, 8, 9 and 10. And then you have a parabolic tetrahedron with curved edges, which is used more to approximate geometries which are having highly contoured geometries. Then you apply constraints, which are different kinds, that is fixed, frictionless surface, pinned surface, or a definite displacement. Then you apply similarly load, maybe it can be surface force, point force, pressure, bearing load, etc. And then you interpret your results. Now using this FEA simulation, we can see we have moved from geometry 1 to geometry 2, which has reduced the material, reduced the print time, and effectively has also reduced the cost. Now let us move to some of the sample problems. So we'll go through them one by one. Okay. So I hope you guys go along with me and answer the questions. Try to answer them at least. Okay, so question 1. Dash is the use of computer systems to plan, manage and control the operations of a manufacturing plant through either direct or indirect computer interface with the plant's production resources. CAD, CAM, both CAD and CAM, or none of these. So, Mr. Vedant, what do you think is the correct answer? CAM. Correct. The correct answer is CAM. So, CAD is mainly associated with the designing process. This is mainly associated with designing, wherein you have your synthesis of the product, and you have analysis of the product design. And whereas this CAM, it is associated with the entire manufacturing of the product using numeric controls and etc. So, and since it is CAM, it requires computers. So, question 2. The product begins with a need which is identified based on customers and market's demands. True or false? Mr. S. Kavi. Okay, Mr. Vedant, is it true or false? What do you think? True, correct. If there was no need for a product, why would anything be designed or manufactured? So, a product begins with need, which is identified based on customers and market demands. And if the demands are not considered in manufacturing or designing a product, then it's of no use. It's just garbage. Question 3. Which of the following processes come under CAM? Quality control, design evaluation, design conceptualization, or all of these? So, Mr. Vedant, what should be the correct answer? Okay, all of these. Okay, so the correct answer is actually quality control. Okay, quality control comes under CAM, but your design evaluation and design conceptualization, these are your part of CAD. Okay, so design conceptualization. this comes under synthesis subpart of CAD, and this design evaluation, this comes under analysis part of CAD. Okay, so I think to clear the confusion, we can go back to the first slide. So this one. So their options were design evaluation, which comes under the analysis part. So you evaluate your design based on your simulations or analysis. Okay, you thought quality control comes under post production. Okay, I'll come to that. And then your design conceptualization is in the synthesis part, wherein you go towards actually making your component. And this your quality control, this is a part of your CAM. So after you have manufactured your component, it is very necessary to check if that is as per the quality standards or not before it goes actually into the market. So it is done in the CAM part. So I hope the confusion is clear, Mr. Vedant. Okay, let's move forward. Question 4. Which of the following processes comes under CAD? Design evaluation, design analysis, design conceptualization, or all of these? I hope you can answer this now, Mr. Vedant. Uh, what should be the correct answer? Okay, so as we had seen from the previous question, design evaluation and design conceptualization are a part of CAD, and design analysis is also a part of CAD. As okay, after analysis only we go to evaluation. So all of these is the correct answer. Yes, all of these is the correct answer. So moving on to question 5. Which of the following sub-processes constitute the design process? Synthesis, analysis, both of these, or none of these? Mr. Vedant? Synthesis will be the synthesis of your product design. Okay, synthesis is conceptualization of a design based on the requirements. And analysis is basically analysis of the design to check its feasibility and functionality. So both of these come under the design process. So to clear the confusion again, we'll go back to that chart in slide 1, as Mr. Vedant has answered it as synthesis. Okay, so here you see analysis part and synthesis parts. These are both the sub parts of the CAD process only, wherein in synthesis you have your design ready and then that is analyzed in the analysis sub part of the CAD to check if it is functioning well or not. Okay, so both are a sub part of CAD process only, and CAM is a different process wherein you go to the manufacturer, your part is produced and quality, then it is checked for quality standards, packed and shipped. Okay. Okay. So in the options we had analysis and synthesis both. So correct answer will be both of these. Now moving on to question 6. Which of the following CAD tools is or are required for design conceptualization? Tolerances, numeric control, geometric modeling techniques, or all of these? Okay, so I think this is a bit trickier one. Mr. Vedant? Yes, geometric modeling techniques, correct. So tolerances are more associated with your manufacturing process, wherein every machine and every component has certain tolerances. So if you want to make a hole of say 20 mm, so it can never be exact 20 mm, it can be some 20 plus minus 0.01 mm. So these are the tolerances which are always there as per the machine. And NC stands for numeric control, which is the controlling system of a manufacturing machine. So the correct answer is geometric modeling techniques, which is basically how you can model your designs. So next question, which of the following CAM tools is or are required for inspection? CAPP techniques, NC programming, CAQ, or all of these? Mr. Vedant? So as we are moving ahead, the questions are becoming a bit trickier. So CAPP techniques are computer aided process planning. So these techniques help you to define the manufacturing process. Yes, you are right. It is CAQ. So CAPP helps you to define the manufacturing process, as to you need to turn your component first, then drilling, then maybe milling, etc. So what should be the flow of events in a manufacturing cycle, that is decided by CAPP. Then is your NC programming. Okay. Then is your NC programming. NC programming is your numerical control. It is to direct the machine how to move its tool to the tool path. Okay. And then you have CAQ. CAQ stands for computer aided quality control. So this technique helps you to check if the product is matching with the quality standards or not. So correct answer is CAQ. Let's move to question 8. Which of the following objectives is or are served by graphical kernel system? First, to provide complete range of graphical facilities in 2D, including interactive capabilities. To control all types of graphic devices such as plotters and display devices in a consistent manner. And to be small enough for a variety of programs, or all of these. Okay. Mr. Vedant, would you like to answer this? Okay, you say A. to provide complete range of graphical facilities in 2D, including the interactive capability. Yes, this is one of the objective which is served by graphical kernel system, wherein it provides graphical 2D facilities in the form of 2D objects such as bars, arcs, pie slices, circles. But it also allows us to control all type of graphic devices such as plotters and display, because since it is providing us facilities in 2D, these plotters and display devices, they are also 2D devices, and then they are small enough for a variety of programs. That is, these systems or these file types are very small, that they can be interchanged with between different softwares and machining platforms very easily. So the correct answer is all of these. So Mr. Vedant, is there any doubt in this question? Should I explain it more? Okay. Moving on to ninth question. Geometric modeling is an external part to product design. True or false? Uh, what should it be? True or false, Mr. Vedant? Geometric modeling. Is it associated with product design, or it is an external part? That is, it doesn't have anything to do with product design. Correct. The answer is false. So geometric modeling is closely associated with product design, as without geometric modeling you cannot have your product. You cannot design anything. So the last question for today, which of the following function is performed in design analysis? Automatic dimensioning, automatic mesh generation for finite element analysis, automatic production of shaded images, or all of these? Mr. Vedant, what do you think should be the correct answer? Correct. Correct answer is B, automatic mesh generation for finite element analysis. Since we are talking about the design analysis, we are talking about FEA, finite element analysis. And we do not have anything related to dimensioning or shaded images in FEA. All we do is we have the CAD geometry which we apply, to which we apply the materials, then generate the mesh, apply constraints, loads. So CAD geometry, then material selection, then you have mesh, constraints, then loads, and then results. So here you have nothing related to dimensions or production of shaded images. It is about mesh generation. So these were the questions for today. In case you have any doubts, you can ask them up now, if anything is left. Or else we can wrap up this session. Mr. S. Kavi, do you have any questions? Mr. Vedant, do you have any questions, or we can wrap this up? Okay. Okay, so I think we can end this session now since nobody is having doubts or any questions. So this video will be available to you through YouTube link and these slides through Google Drive links. You can access them anytime and revisit the lectures. So thank you for joining in and interacting. Hope to see you in the last session as well. That is on next week. Thank you for joining in. Okay, so I'll end this meeting now. Thank you everyone.